So at the end of the last video, we were talking about the structure of the atom, and we mentioned that we have in the atom, a typical atom, we have one or more protons, which we call the nucleus, combined with sometimes, or most of the time actually, several neutrons as well. And around this nucleus we have the electrons, which form something of a cloud. That is the part of the atom that actually interacts with the rest of the world for the most part. What we need to add to that is we want to know what keeps these electrons in this electron cloud orbiting that nucleus. And it comes down to electrical charges that are opposites, and as you may have heard before, opposites tend to attract. So the electron, in fact, has a negative charge, so let's put a little negative sign over there next to the electron. And then, of course, the proton would have the opposite charge, which is a positive. Okay, so we have a positive proton and a negative electron, and opposites attract, so the protons are attracting the nucleus and keeping them in something that is referred to as orbitals. We tend to call them orbits in everyday language, but in fact it's not like the planets orbiting the sun. It's a rather different concept, but for one thing, it's three-dimensional spherical orbit rather than a two-dimensional plane that the planets orbit on. The neutron itself, however, as the name suggests, is actually neutral. It has neither a positive nor a negative charge, so it does not contribute to the total charge of the atom, and it has no influence over the electrons either. So once again, the two main parts of the nucleus, the protons and the neutrons. Protons are positive, protons are positive, neutrons are neutral, and electrons are negatively charged. Okay. Next, we have the fact that most atoms, when we talk about individual atoms and what the structure of an individual atom is, it sort of it hides the fact that most of the substances that we are familiar with are not individual atoms, but atoms that are bonded to other things. These partnerships between atoms can either form molecules or compounds depending on what kind of substances are involved. So in this picture we see a hydrogen molecule, and the hydrogen molecule, as you can see here, it consists entirely of a single proton in this hydrogen atom orbited by a single electron, and over here another hydrogen atom with its single proton orbited by its single electron. But when two hydrogens get together, they actually want to share their electrons so that they each have two electrons in that particular shell. So they're sharing an electron, and that sharing of the electron is what forms a bond. The water molecule, as you can see here, these diagrams are showing you the electron configuration. So oxygen is this larger molecule, or this larger atom. It has two electrons in this shell, this orbital shell, and it has 6 electrons in the other orbital shell. And as you can see here, what it's doing when it gets together with hydrogen under the right circumstances, it will actually form a bond with hydrogen to make water molecules, and it actually wants to share its electrons with 2 hydrogens to give us hydrogen, H2O. All right. Moving along to the next part here, the structure. Here we take a closer look at a water molecule. Water is going to be extremely important to our understanding of biology, so we'll spend some time talking about water molecules, and we'll do a lab on one of the very important characteristics of water molecules later on next week. So what you see here is a water molecule. Now the total molecule itself, the total charge here is 0. So the molecule itself is neutral. And that means that it has the same number of protons as a molecule as it does electrons. So the oxygen contributes 8 protons and 8 electrons, and the hydrogens have 1 proton and 1 electron each. So again, all of those things balance out. But it turns out that oxygen is something of an electron hog. So the hydrogen electrons tend to spend more time in here with the oxygen than they do with the hydrogen, which gives the water molecule what's referred to as a partial charge, and therefore it has a negative pole as you can see down here, with the tendency of the electron to hog, of the oxygen to hog the electrons. It has then therefore a negative pole, and it has a positive pole, which is where the protons of the hydrogen molecule pole, and that tends to have a slightly positive charge on this end. And if you know anything about poles, you've heard of poles before. Most likely you've heard of poles in terms of magnets. So in magnets, you know that there's a north pole and a south pole, and you know that the north and the south pole of one magnet are attracted to the opposite poles of another magnet. In other words, the north pole of one magnet will be attracted to the south pole of another magnet. The water molecule works in a similar way in that the negative pole of one water molecule is attracted to the positive pole of another water molecule. And we actually have a special name for that we'll get to in a couple of minutes. But I just want you to see the overall structure of the water molecule is that it has both a positive and a negative pole, and that accounts for a lot of the unusual characteristics of water that we'll talk about soon. All right. But let's go back again just a little bit back from where we were. Most substances that you're familiar with are actually mixtures and not pure substances. A pure substance is really defined as a compound or a molecule or an element. So pure substances are compounds, molecules, and I guess I should start on this side with elements. Elements, compounds, and molecules. Anything else is going to be a mixture of things. So you take a bunch of elements and compounds and molecules and throw them together in a place, and you get basically a mixture. So one of the most common ones, of course, is air. Air is not a pure substance, it's a mixture. Most water that you find on Earth in lakes and rivers and streams and oceans, that's a mixture and not a pure substance. It's not pure water, it's water that's got a lot of things dissolved in it. But what are the things, of course, that we can have that can be mixed together? An element I just mentioned would be a pure substance that's only made up of one atom, or found in its elemental form. You have something like O2, which is how oxygen is traditionally found in its pure form on Earth. A compound would be if you take two different elements such as hydrogen and oxygen and they combine in a chemical way, then you have what's referred to as a compound. And compounds can either be molecules like you have with H2O here, that's a compound, that's also a molecule, or it could be something like sodium chloride, which is a compound but it's not a molecule, it's actually an ionic compound, and we'll get more of that in just one second. All right, so the elements that we have, there are only about 92 of them that exist naturally on Earth. The others have been synthesized artificially in laboratories. There are only a few atoms that exist alone. Most of them like to form bonds with other substances. The only things that don't like to form bonds with other atoms are called the noble gases. Some of these you've heard of before. Noble gases such as helium, which you've heard of before, and argon, and what's the other one that you've all heard of? Neon, like they put in neon signs and so on. That neon signs actually do have neon in them, and some other gases depending on what color they are. All right, so these are the ones that don't like to form bonds with other things. Most of them, however, other atoms like to form bonds. Typically, energy is required to create chemical bonds, and when chemical bonds are broken, energy is released or made available for other purposes. And the two most important of those types of reactions for us in biology are photosynthesis. And in photosynthesis, we're going to make some chemical bonds, or I shouldn't say we, plants. Plants are going to make chemical bonds, and they're going to need energy for that, and that energy they will get from the light. And photo is the Greek word for light. And respiration is the one that we use. Plants also use it, but we don't use photosynthesis. So respiration, of these two, respiration is the only one that we can use. And respiration is the breaking of the chemical bonds. So here we're going to break some chemical bonds and we're going to get some energy for it that we need in order to stay alive and to do our body functions and life processes.